Welcome viewers to the fourth and the last segment of the sixth lecture for the online series of lectures for the course of linear algebra. Towards the end of the previous segment, we described the general method for answering the three questions posed with relation to computations of subspaces. Okay, in this segment, we are going to give you an example demonstrating the application of that general method. Example 3. Let W be the subspace of R to the 4 spanned by the following three vectors. Alpha 1 is the fourth tuple 1, 2, 2, 1. Alpha 2 is the fourth tuple 0, 2, 0, 1. And alpha 3 is the fourth tuple -2, 0, -4, 3. Okay. First, prove that alpha 1, alpha 2, alpha 3 form a basis for W. That is, that these vectors are linearly independent. Okay, that's the first part. In the second part, let beta is the fourth tuple given by B1, B2, B3, B4. This vector be a vector in W. W is the subspace of R4 spanned by these three vectors, alpha 1, alpha 2, and alpha 3. What are the coordinates of beta? Of this vector beta relative to the ordered basis alpha 1, alpha 2, alpha 3. Okay, so that's the second question. In the third part, let alpha 1 prime is equal to the fourth tuple 1, 0, 2, 0. Alpha 2 prime is the fourth tuple 4, 0, 2, 0, 1. And alpha 3 prime is the fourth tuple 0, 0, 0, 3. Okay, show that alpha 1 prime, alpha 2 prime, alpha 3 prime form a basis for W. Okay. D, in the fourth part, if beta is the generic vector of the subspace W spanned by the vectors alpha 1, alpha 2, and alpha 3, let X denote the coordinate matrix of this vector beta relative to the alpha basis. Okay, and X prime the coordinate matrix that matrix of beta relative to the alpha prime basis. Find the 3 times 3 matrix P such that x is equal to px prime for every beta in the subspace W of R to the 4. Okay? These are the 4 questions that one needs to answer. Let me erase everything. Now that we have the question, let us look for the answers. Okay. So in order to answer these questions according to the general method described in the previous segment, we form the matrix A, okay, with row vectors alpha 1, alpha 2, alpha 3. Okay, and find the row reduced echelon matrix R, which is row equivalent to this matrix A to A. Okay, and simultaneously perform the same elementary row operations the same EROs on 3 times 3 identity matrix to obtain the invertible matrix Q such that Q is equal to such that this row reduced echelon matrix R is equal to Q times the original matrix A, whose rows are these 3 vectors in R to the 4. Okay, so let us find the row reduced echelon matrix, starting with the matrix A first. So let us form this matrix A first, which is this 3 times 4 matrix 1 2 2 1. Then alpha 2 is 0 2 0 1, and alpha 3 is minus 2 0 minus 4, 3. This is matrix A. The first elementary row operation that we perform on this matrix A is 2R1 plus R3 is equal to R3 prime. Okay, so we multiply this the first row with 2 and then add it to the third row to find the new third row. So the first row and the second row stay the same, 1 2 2 1, 0 2 0 1, and this is 0, this is 4, right? And then this is 0, and this should be 5. Okay, good. Now we apply the following elementary row operations on this matrix. Minus R2 plus R1 is going to be equal to R1 prime, and minus 2R2 plus R3 is equal to R3 prime. Okay. The second row stays the same this time. 0 2 0 1. Okay. And the first row, so we multiply the second row with minus 1 and add it to the first row to have the new first row. So this is going to be 1, and this is 0 now, and this is 2, and this is 0. Okay, and in this case this is 0, this is 0, this is 0, this is minus 2 plus 5, 3. Okay, now we multiply the third row with 1/3 to obtain the new third row. We get 1 0 2 0 0 2 0 1, and then we have 0 0 0 1, right? And then we apply minus R3 plus R2 is equal to R2 prime. That leaves us with this matrix. We multiply the third row with minus 1 and add it to the second row to obtain the new second row. So first row stays unchanged 1 0 2 0. Then we have 0 2 0 0, and then we have 0 0 0 1. Finally, we apply this operation. One half R2 is equal to R2 prime. That leaves us with the following matrix: 1 0 2 0 0 1 0 0 0 0 0 1. This is this is in row reduced echelon form, right? So this is our matrix R. Okay, so now we have to apply the same sequence of elementary row operations on that 3 times 3 identity matrix. Okay, let's do this. So we start with the matrix 1 0 0 0 1 0 and 0 0 1. First we apply this operation. 2R1 plus R3 is equal to R3 prime, and this gives us, so the first row stays the same, the second row stays the same, and the new third row is going to be 2, 0, 1, right? Now we apply these two operations. Minus R2 plus R1 is equal to R1 prime, and minus 2 R2 plus R3 is equal to R3 prime, to end up with the following 3 times 3 matrix. So there is 1 here, there is minus 1 here, and there is 0 here, and the second row stays the same, 0, 1, 0. And the third row, new third row becomes, this is 2, this is minus 2, and this is 1, right? Right. Then we apply this elementary row operation on this 3 times 3 matrix. 1 over 3 times R3 is equal to R3 prime, to obtain the following 3 times 3 matrix. 1, minus 1, 0. Then we have 0, 1, 0, and 2 over 3, right? 2 over 3, minus 2 over 3, 1 over 3. Okay. All right. Now we apply this operation, minus R3 plus R2 equal to R2 prime, and that leaves us with the following 3 times 3 matrix. The first row stays the same, 1, minus 1, 0. So the new second row is going to be minus 2 over 3, and so I multiplied minus 2 over 3 with minus 1 to get 2 over 3, and when that gets added to 1, we have 5 over 3. 5 over 3. Okay. So when we multiply the 1 third with minus 1, negative 1 third, negative 1 third getting added to 0, gives us negative 1 third, right? Negative 1 third. The third row stays the same, 2 over 3, negative 2 over 3, and 1 third. So finally, we multiply the second row with 1 half to obtain the new second row. 1, minus 1, 0, and this is negative 1 third. This is 5 over 6. This is 5 over 6. Okay. And this is negative 1 over 6, right? And the third row stays the same, 2 over 3, negative 2 over 3, and 1 over 3. So this final matrix can be simplified further by multiplying, this matrix is the same as 1 over 6 times the following matrix. So everything gets multiplied with 6, all the entries. So this is 6, this is minus 6, this is 0. So if I multiply negative 1 third with 6, then I have minus 2. Then this is plus 5, this is minus 1, and then this is 4, this is minus 4, and finally when I multiply 1 third with 6, I get 2, plus 2. So this is the final matrix. Okay. So so the claim is that this matrix R is we call this matrix Q. Okay. So R, this 3 times 4 matrix, 1 0 2 0 0 1 0 0 0 0 0 1. This is the row reduced echelon matrix, and this matrix R is equal to Q, which is 1 over 6 times this matrix 6 minus 6 0 minus 2 5 minus 1 and 4 minus 4 2. This matrix is Q times the matrix A, right? This is the matrix that we started with. 1 2 2 1 0 2 0 1 minus 2 0 minus 4 3. Okay, so this is a 3 times 3 matrix, and this is a 3 times 4 matrix, and the resulting matrix is going to be a 3 times 4 matrix. And you can check that this 3 times 4 matrix is indeed this matrix on the left hand side. Okay, so it should be equal. So now I give you the reason why this method works. Why Q is equal to why R is equal to Q times A. Why does it work? Okay, so explicitly you can check that this equality holds in this case. So let me explain why this thing works. Okay. So here, so remember that how we obtain Q? We obtain Q by applying the same elementary row operations on the identity matrix I. The operations that one applies on the matrix A to get to the row reduced echelon matrix R. Okay, so if one applies those operations in the same sequence on the identity matrix, one arrives at that matrix Q. Okay, and if one obtains the Q, matrix Q in this way, then R is going to be equal to Q times A. Okay, so here one writes Q as Q times I, the identity matrix. Okay, now the point is that this Q is going to be product of some elementary matrices. Product of elementary matrices. Why? Because this Q is row equivalent to I, right? You get Q from I by applying a finite sequence of elementary row operations, which means that Q is row equivalent to I, and from our knowledge on elementary row operations and elementary matrices, we know that this matrix Q is going to be a product of elementary matrices, a finite product of some elementary matrices. In words, after performing a set of elementary row operations on I, okay, one reaches the matrix Q. that is Q is equal to ES dot 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 E2 times E1 times I. Okay, so these are S. There are S many elementary matrices in this product. Okay, so this is the product of elementary matrices. Okay, now, or in terms of elementary row operations, one can translate it, or in terms of elementary row operations, Q is equal to ES dot 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 E2 E1 of I, closing the brackets in appropriate order. Okay, so it means that you first apply the elementary row operation E1 on the identity matrix I, and then you obtain a 3 times 3 matrix, right, on which you apply E2 to obtain another matrix, another 3 times 3 matrix, and you keep on applying this elementary row operations until you finally apply the elementary row operation ES on a certain 3 times 3 matrix. Okay, now given the matrix A, so we are given a matrix A, a 3 times 4 matrix, right? Now, given the matrix A by theorem 2 of lecture 4, E1 of A is going to be equal to E1 times A, where E1 is an elementary matrix. Okay, of appropriate size. Okay, in this case it's a 3 times 3 matrix. So if you choose the A to be the if you choose A to be a 3 times 4 matrix, the way we had it in our example, then E1 is going to be a 3 times 3 matrix, 3 times 3 elementary matrix. Okay, then you apply E2 on E1 of A, and that is the same as E2 times E1 times A. Okay. Therefore, the successive application of these elementary row operations on A is equivalent to the product of these elementary matrices with A. And this is nothing. We know that this guy is R, the row reduced echelon matrix. Okay, so we have seen that Q, right, sorry, so therefore R is equal to ES dot dot E2 E1 times A, right? So this is going to be equal to that. but we have shown that es dot 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 e2 times e1 times I is q, so that we have R to be equal to q times A. Okay, so we obtain, so therefore we obtain q by applying the same set of elementary row operations on I as the ones applied on A to obtain the row reduced echelon matrix R, right? Good. So this is the explanation to why R is equal to Q times A. Okay. Now, now that we have all the materials at our disposal, we proceed to solve the problem. Solution of part A. Since there are three non-zero rows in R, three non-zero rows in the row reduced echelon matrix, it means that, A has row rank 3. In other words, the row space of the matrix A is three-dimensional. Okay, it has A has row rank 3. Hence, the three vectors alpha 1, alpha 2, alpha 3 forming the matrix A, whose rows are of course alpha 1, alpha 2 and alpha 3, are linearly independent. Hence, alpha 1, alpha 2, alpha 3 are linearly independent. So we just check that these three vectors are linearly independent. So we are done with the solution of part A. Now solution for the part B. So W is the a subspace of R to the 4 spanned by these three linearly independent vectors, alpha 1, alpha 2 and alpha 3. A basis for this subspace of R to the 4, W, is given by the non-zero vectors. So all three vectors are non-zero in the row reduced echelon matrix R, and those are the basis elements, right? The row vectors of R. One therefore writes for any vector B in this subspace W, beta can be written down as B1 row 1 plus B2 row 2 plus B4 row 3. Let me explain why we have these three coefficients B1, B2 and B4. Why B3 is absent. Okay, let me explain. So let me write down this row reduced echelon matrix that we obtained. In our case, this was 1 0 2 0, then we had 0 1 0 0, then we had 0 0 0 1. Okay, this was the row reduced echelon matrix. These are the leading ones. Okay, so in this case, so if we recall the general method that we had described in towards the end of the previous segment, according to the general method, this is K1, right? This, so sorry, this leading one corresponds to K1, and K1 is the first column for which K1 is equal to 1, and K2 is equal to 2 because it occurs in the second column. And what is K3? So K3 is K3 because it applies to the third row. That's why we call it K3, and K3 is equal to the fourth column. Right? So K3 is equal to 4 because this leading one on the third row occurs in the fourth column. That's why K3 is equal to 4. Okay. So using 26, so let us recall equation number 26. It was beta is equal to, from I equal to 1 to R, B sub Ki rho I, right? This was the expression. So from which, so here this is equal to B sub K1 rho 1 plus B sub K2 rho 2, and there is the final one is B sub K3. So here R is 3 in our case. B sub K3 rho 3, right? What is B sub K1? K1 is what? K1 in our case is 1. So this is B1 rho 1, and K2 is 2. So this is B sub 2, B2 rho 2, and K3 is 4. So we have B4 rho 3. Okay. Therefore, we see that beta is nothing but this vector written in the matrix form B1, B2, B4. This is a row vector, and then there is a column vector containing this non-zero rows of the row reduced echelon matrix, row 1, row 2, and row 3. Okay. So if we plug in the values of row, so the expressions for row 1, row 2, and row 3 here, let's do that. B1 times, what is row 1? Row 1 is 1020, right? 1, 0, 2, 0. And then this B2 times, what is row 2? Row 2 is 0, 1, 0, 0. And then finally we have B4 times, what is row 3? 0, 0, 0, 1. Okay, so that we have B1, the first component, and the second component is going to be B2, and the third component is 2B1, and the fourth component is B4. This is how this vector beta looks like. So this is the span. So this is a general element of the span of these three vectors, row 1, row 2, row 3. Okay, so the span of these three vectors consists of the vectors beta equal to b1, b2, b3, b4 with b3 is equal to 2b1. This is what we have found, okay, from the general expression of beta given by this expression. Okay, good. Now, okay, let me erase these things here. Let me erase everything. So this vector beta, which is an element in the span of these three vectors rho1, rho2, rho3, is equal to b1, b2, b4 times the row reduced echelon matrix R, okay, which we wrote earlier as the collection of these three row vectors, okay, this way. But now let's write it as R, where R is the row reduced echelon matrix whose non-zero rows are row 1, row 2, and row 3. Okay, so we have seen earlier that R can be written down as Q times A. We have this explicit expression of Q. So B1, B2, B4 times Q times A, okay, which means that this is equal to B1, B2, B4 times Q times, what is A? A is the collection, A is, the collection of the three row vectors, alpha 1, alpha 2, and alpha 3, right? So we write it as this column matrix, where alpha 1, alpha 2, and alpha 3 are the row vectors, which are the rows of the matrix A. Okay, and this is equal to x1 alpha 1 plus x2 alpha 2 plus x3 alpha 3, right, which is written as x1 x2 x3 times alpha 1 alpha 2 alpha 3, okay, so that b1 b2 b4 times qi is going to be equal to xi, where I runs from 1 to 3. Okay, so it's important to write it here. Q is equal to Q1, Q2, Q3. So these are three columns of Q1, Q2, Q3 are columns of Q in this expression. Okay, so that therefore one obtains in this special case, in this case, B1 b2 b4 times, so q1, we have this explicit expression of q, right? So let me get back to the expression of q. Q was this. So q1 is the first column of the matrix q, which is 1, negative 1/3, negative 1/3, and 4/6, or 2/3, right? 2/3. And this is going to be equal to x1, right? So I'm just plugging in 1 here. So x1 is this guy, so which implies x1 is equal to b1 minus 1/3 b2 plus 2/3 b4. Okay. Now b1 b2 b4 times this second column of q, right, which is minus 1, 5/6, and then minus 2/3, and that is equal to x2, which implies x2 is equal to minus b1 plus 5/6 b2 minus 2/3 b4. This is x2. Okay, so let me erase everything here. Now b1 b2 b4 times the third column of q, which is 0 minus 1/6, and then 2/6, which is 1/3, and this is equal to x3, which means x3 is equal to negative 1/6 b2 plus 1/3 b4. So one finally gets the following system of linear equations. x1 is equal to b1 minus 1/3 b2 plus 2/3 b4. Okay, and x2 is equal to minus b1 plus 5/6 b2 minus 2/3 b4. Okay, and finally x3 is equal to minus 1/6 b2 plus 1/3 b4. This is what we call equation number 27. Okay, good. Okay, so this is the solution of part B. Okay, so the coordinates of beta relative to the bases alpha 1, alpha 2, and alpha 3 are x1, x2, and x3. So this is how we write x1, x2, and x3 in terms of the coordinates b1, b2, and b3. Sorry, b1, b2, and b4, which are the components or the coordinates of this of this vector beta. Okay. Good. So now part C. For part C, solution of part C, so one can form the matrix A prime by taking the rows of this matrix A prime to be the vectors alpha 1 prime, alpha 2 prime, and alpha 3 prime respectively. Okay, so alpha 1 prime was 1 0 2 0, right? Let me check. Yes, alpha 2 prime was 0 2 0 1, and alpha 3 prime was 0 0 0 3. Okay, so taking these 3 row vectors, we can form this 3 times 4 matrix, which we call A prime. And notice that A prime is row equivalent to our original matrix, original 3 times 4 matrix A, right? When we try to row reduce the original matrix A to put it into a row reduced echelon form R, we saw that in one of the intermediate steps we reached this matrix. Okay, go back and check that you reached this matrix at some point. Okay, at some point before reaching the final row reduced echelon matrix R. Okay, which means that our original matrix A is row equivalent to this matrix A prime. Okay, since A is of row rank 3, A prime, this matrix, is also of row rank 3. Hence the vectors alpha 1 prime, alpha 2 prime, and alpha 3 prime has to be linearly independent as well, right? Because this is of rank 3. What does it mean? It means that since the subspace W is spanned by these 3 vectors, alpha 1 prime, alpha 2 prime, and alpha 3 prime, and these 3 vectors are linearly independent, meaning that alpha 1 prime, alpha 2 prime, and alpha 3 prime, these 3 vectors form a basis of the subspace W spanned by the 3 vectors alpha 1 prime, alpha 2 prime, and alpha 3 prime, or alpha 1, alpha 2, and alpha 3. They're the same space which we call by W. Okay. To answer the question for this part C, the 3 vectors alpha 1 prime, alpha 2 prime, and alpha 3 prime are linearly independent and they form a basis for W. Okay, for part D, the final part of this example 3, solution of part D. From the theorem 3 in this lecture, we know that we denoted by Pj, which is the jth column of this invertible matrix B, which is the same as the coordinate matrix of alpha j prime, alpha prime j, relative to the basis B. Okay, so in this case, since we are dealing with a 3 times 3 matrix, okay, it's going so it's going to be a 3 times 3 matrix, right, in this case, right? So this is the jth column of this 3 times 3 matrix, P1j, P2j, and P3j, right? This is the jth column of the 3 times 3 invertible matrix P. Okay, so I ask you to have a look at equation 13 prime. Have a look. Good. Where this basis B is alpha 1, alpha 2, alpha 3. Okay, so we know that beta, this vector, a generic vector of the subspace W, right, is given by B1 row 1 vector plus B2 row 2 vector plus B4 row 3 vector. Okay, take so in this special case we take this vector beta to be alpha 1 prime. Okay, and we know that alpha 1 prime is given by this 1 0 2 0, right, this row vector, and we want 1 0 2 0 to be equal to B1 times the vector row 1, right, 1 0 2 0 plus B2, but is row 2. Row 2 is 0 1 0 0, right, plus B4, what is row 3. Row 3 is 0 0 0 1. Okay, this is what we want, which means B1 is equal to 1, right? B2 is equal to 0. And what is B4? Well, B4 is also 0. So plugging in these values, in 27. Okay, so if you don't remember 27 is the equation, 3 linear equations relating x's to b's. Okay, so let me write the equation here, x1, so which we derived in part B. x1 is equal to b1 minus 1 over 3 b2 plus 2 over 3 b4. And x2 was minus b1 x2 was minus b1 plus 5 over 6 b2 minus 2 over 3 b4, and x3 was negative 1 over 6 b2 plus 1 over 3 b4. This was 27. So plugging in these values of b's in 27, we get x1 to be equal to, so b1 is 1, so x1 is 1, right? and x2. So b1 is 1, b2 is 0, b4, so this is minus 1, right? And what is x3? x3 is 0. Since both b2 and b4 are 0, x3 is 0. This is our equation number 28. So let me clear this part. So from 28, it follows that alpha 1 prime, okay, we took beta to be alpha 1 prime, right? Alpha 1 prime is equal to x1 alpha 1 plus x2 alpha 2 plus x3 alpha 3, right? And according to what we have gotten so far, so plugging in these values of x1, x2, and x3 here, we got alpha 1 prime to be equal to alpha 1 minus alpha 2. Okay? Now, following exactly the same procedure, now take beta to be alpha 2 prime, which is this vector, this row vector 0 to 0, 1. Okay, in this case 0 to 0, 1 is going to be b1, and then I'm writing row 1, 1 0 2 0, and b2 times row 2, which is 0 1 0 0, and plus b4 times row 3, right? Row 3 is 0 0 0 1. Okay, from which we see that b1 is equal to 0, b2 is equal to 2, and b4 is equal to 1. So plugging in these values again in 27 gives us, one checks that x1 is equal to 0, x2 is equal to 1, and x3 is equal to 0, right? So which means that, so alpha 2 prime is supposed to be x1 alpha 1 plus x2 alpha 2 plus x3 alpha 3, right? So plugging in these values of x1, x2, and x3 here, we see that alpha 2 prime is going to be equal to alpha 2. Okay? And, exactly applying exactly the same method, we find that alpha 3 prime is equal to 2 alpha 1 plus minus 2 alpha 2 plus alpha 3. Okay? So this is alpha 3 prime. And this is alpha 1 prime. One therefore has the coordinate matrix of alpha 1 prime with reference to, relative to the basis B. Okay? Is going to be equal to is going to be equal to 1 minus 1 0. 1 minus 1 0, and the coordinate matrix of alpha 2 prime relative to the basis B, okay, relative to this basis B, where B is this, right? B is this basis, alpha 1, alpha 2, alpha 3. Okay. So relative to this basis B is so the expression of alpha 2 prime is just alpha 2, so which means that this is 0, 1, 0. And the coordinate matrix of alpha 3 prime relative to this basis B is equal to this 2 minus 2 plus 1. Okay, so which means that if I write this invertible matrix P, then the first column of this matrix P is going to be this column vector, and the second column of this matrix P is going to be this column vector, and the third column of P is this column vector. So P can be written down neatly as 1 minus 1 0, 0 1 0, and 2 minus 2 1. Okay, and we are done. We are supposed to find this matrix P. Okay, between the the transition matrix between the alpha basis and the alpha prime basis. Good. All right, now a bunch of suggested exercises as before. Suggested exercises from the same book, Hoffman and Coons, page number 66, problem number 2, number 3, number 4, number 5, and number 6. 5 problems as before. Okay, so this is the end of lecture 6. Thank you for attending the 6th lecture.